let me share the screen then. Let me find what I want to share here.
Okay, so dear Professor Cabana, that's a real pleasure for you, that for me, for us, that you accept to give these lectures and for the project Ecodep. And really, I hope that we have some occasion to see again soon. So thank you for giving those lectures.
Okay, well, thank you, Paul, for having invited me to do this and for engaging with this super interesting project. Congratulations for that too, especially in this complicated moment for all of us. Cannot travel, cannot do most of the things we were used to. So, well, let me begin with this. I will do something very, I'm going to talk about count time series, which should be a very well-known subject because since the publication of Box and Jenkins' book 50 years ago, exactly 50 years ago, a lot has been said about time series, but in general, for count time series, the subject is less known because up to a couple of years ago, there were no textbooks on the subject. So I'm going to do a sort of index of a textbook of a book on count time series. So everything that I'm going to explain now is very, very simple. There are more complicated stuff on the subject, of course, but it's just to give you the hint that there are a lot of things to do here. And a lot of things have been done, and there's more things to be done in the future. So, well, let's go. As I said, there are many, I cannot change with my arrows here. Okay, so the overview of the course of today's lecture will be talk about stationary count time series. There are essentially 3 ways, which I'm going to cover, only 2 of the main 3 ways of dealing with that, which are thinning-based methods and conditional regression models. And for next lecture, if you still hold with me, we are going to talk about some new stuff we have been doing on the subject for dealing with underreporting of count time series. Okay, so let's begin with what a count time series is. So imagine what we have is a series of observations, x1 to xt, from a univariate time series that originates from a stationary count process. So there are many constraints here. One of them is that the observations are natural numbers, non-negative integers, and the other one is that the process that generates it evolves in time, preserving at least first and second order moments. I mean, it's a stationary count process. We will see later how to deal with non-stationarity because most processes you find with real data are not stationary, of course, but let's begin by modeling stationary count processes. Okay, so first thing you do when you have a problem like this is to, well, check marginal characteristics, and based on the marginal characteristics, try to define models for the model, how to model it, and then how to do the fitting, I mean, how to estimate the parameters, how to do diagnostics, whether to see if the model fits the data reasonably enough or not, and then try to make some forecast. And well, that's the plan. So in general, theoretical aspects of count time series modeling are very technical, and essentially because since the observations are discrete value, they might be problems with the mixing conditions. So many work has been done, most of it by Paul Lucan himself. So I'm not there to talk about that. He'd better do it. But I'm trying to focus the attention to data analysis tools. So references on this, huge tons of research papers, which are not referenced very precisely here, and see just names of authors and dates, as you can see here. And well, this is statistics and probability letters. Bernoulli is Bernoulli, but there are tons of papers. Theoretical aspects can be found in this handbook of discrete values time series, but it's from 2016. So there are newer stuff that are not there. And then for essentially the three main methods of analyzing this data, we have three books, Zucchini and McDonald, and now Langwork. This is a very nice book that treats count time series as stochastic processes, hidden Markov models. Then there is this book by Kedem and Fokianos, which is from 2002, I guess. I've heard there's a new version of the book, but I haven't been able to find it. And then it's this other book by Christian Weiss, which is this is really a textbook. You can do a regular undergraduate course following this discrete value time series book. So let's end up with the propaganda and begin with some. Okay, so as I said before, there are different approaches for modeling univariate and unbounded count time series. There are methods for multivariate count time series, which I'm not going to talk about. And if the counts are bounded and not unbounded, then many things change as well. And I'm not going to mention that except for maybe an example or not. By bounded counts, I mean, for instance, I don't know, the number of countries in the Eurozone with a given number of, well, or a given percentage of inflation, for instance. The number of countries year by year where the inflation is less than 2%, say. So these are bounded counts. There cannot be more than 17, no, now 16, we have Brexit. So well, the number of countries that have that particularity are bounded. Okay, but we are going to talk about unbounded counts. And as I said before, there are essentially three methods of dealing with this. The one that has been used the most in the past are the hidden Markov models. That's treating the count time series as if it were, well, it is a stochastic process evolving in time, and the different states of the process are the different values of the possible counts. And there are another two methods that try to mimic somehow Boxon-Jenkins ARMA setup. And these are the thinning-based methods and the conditional regression models. And these are the ones that we are going to study here. Okay, so let's begin with the thinning-based methods. So the idea is that when you observe count time series, you often get a set of autocorrelations that are similar to those that appear in the ordinary ARMA setup by Boxon-Jenkins. An ARMA model is something which is written like this, is a linear combination of past observations plus a linear combination of past noises plus an innovation. That's a general form of an ARMA model. And these cannot be directly applied to count processes because, well, in order to get stationary processes, for instance, if you only have an ARMA with one lag dependence on the past, and you don't have these, and you don't have the dependence of past noises except the actual innovation in time t, which is supposed to be Gaussian in Boxon-Jenkins case. Well, if you have something like this, for instance, you have an AR1, in order to have a stationary process, that phi has to be smaller than 1. So if you apply that to a count time process and you put a coefficient smaller than 1 here, even though this, and the noise are integers, then you cannot get an integer, so forget it. So the idea is to modify this in such a way that the process generates only count data, but still the shape of the autocorrelation functions remain more or less like the autocorrelations of the ARMA models. So that's the idea. So, as I said before, there are two ways of doing that. One way is the so-called thinning operations, which is a way to circumvent the problem of multiplication. And well, so what's a thinning? Well, the models that arise from this thinning operation on the past observations and the past noises are called in-ARMA models, integer valued ARMA models. So let's, there are a large variety of possible thinnings operations, but we will concentrate on binomial thinning operator, which is simply for a given alpha, which will be a probability, so it's a number between 0 and 1, and applied to a count variable x, we define the alpha thinning by simply summing up to x a certain number of independent Bernoulli random variables. So conditional on x, what the binomial thinning is a binomial random variable with well, n equal to x, and the probability of success being alpha. So what we get by the alpha thinning is a randomly generated count between 0 and x. And of course, the expectation of alpha x is of the alpha thinning of x will be alpha times the expectation of x. So in that sense, it mimics what happens with the regular ARMA process when we put here the past of the x. This thinning operation is often interpreted as the random number of survivors from a population of size X. For each of the guys, for each of the individuals, up to 1, 2, 3, 4, X, we flip a coin and decide whether the individual remains or doesn't remain. But that interpretation somehow can be misleading when dealing with time series, because we maybe don't want an individual to survive from one generation to the other, but just the number of individuals to be the number of individuals that we had before, somehow thinned by this operation. So the interpretation, for some properties, for some theoretical properties helps, but for the modeling of time series might be confusing. Okay, so expectation and variance of the thinning operation, of the thinning operator, of course, are easily computed just by computing the conditional expectation. So the expectation is the expectation of the conditional expectation. And in that case, if the stopping variable has mean mu and variance sigma squared, then the expected value of the thinning will be alpha times mu, and the variance will be alpha times 1 minus alpha times X. So that, well, the variance of the thinning is alpha square sigma square plus this term here that is added because of the variance of the total variance formula. And based on that, we will define the in R1 model, integer autoregressive model of order 1, still with only one lag in the past and no linear combination of innovations. These processes were defined more or less at the same time by Mackenzie and by Alosh and Al-Said. The problem is that Alosh and Al-Said do it in Journal of Time Series Analysis, and Mackenzie wrote it down in, well, here, Time Series Analysis in Water Resources. So nobody read Mackenzie's paper until these people rediscovered it. So the idea is very simple. Define the process at time n by considering a thinning of an alpha thinning of the previous count, X, observed in n minus 1, plus an innovation, an independent innovation, which will be another non-negative integer valued random variable, independent of the past, and the thinning is the thinning we have defined before. So as we had before, the conditional expectation and variance are readily computed like this. And it's easy to see that this process is an homogeneous Markov chain with transition probabilities given by, well, the convolution of the binomial that we have for the thinning part and the distribution of the noise. So we have this convolution here. And given that, it's easy to see that the conditional expectation and variance are both linear in the previous observation X minus 1. However, the variance, this is exactly what happens in autoregressive process of order 1 in the Boxing-Jenkins style. However, for the variance, for the conditional variance, we have this variance here that doesn't appear before. So this is conditionally heteroscedastic, which doesn't happen with the original AR1. And in order to study possible stationary distributions, we have to observe that that this is a branching process within migration. So it's a sort of Galton-Watson here, plus this immigration term noise here. So if the mean of the offspring distribution is smaller than 1, then we will have a subcritical branching process. And in that case, we have a stationary distribution. So that's what we have. And that also gives us mixing conditions. So that's what we have. A subcritical branching process within migration, which is also an irreducible and aperiodic Markov change with the expectation of the innovation smaller than 1, then we have a proper stationary marginal distribution. This allows to derive mixing properties for these kind of processes. And well, so we have a central limit theorem because in R1 is an alpha mixing process. And that happens with, in fact, the in RP when we grow the number of past models. Well, being said that, I said I was going to concentrate only on binomial thinning, but as I said before, there are other kinds of thinnings that can be used, which will not produce exactly these properties, but marginal properties of other binomial thinnings will show other things. Okay. Okay. Perhaps further assumptions need to be taken care of because all the thinning operations are random. So we need to ask that all the thinning operations are independent, for instance, because we are going to thin all the observations eventually. Okay, so we've talked about stationary distributions. So what about the marginal distribution of the chain, that is the distribution of xn? Well, the mean and the variance are straightforward to compute. I mean, just if we assume that we have a stationary distribution, then take expectation in both sides here, and it's straightforward to see that the mean, the marginal mean will be the mean of the innovations divided by 1 minus alpha, and the variance takes this form. Probability generation function allows us to compute the moments easily. So if there is a stationary distribution for the observations, then the probability generating function satisfies, well, this is the binomial probability generation function, so that's the probability generation function of the binomial multiplied by the probability generating function of the innovations. And with the probability generating functions, then you have almost anything you need for the marginal distribution. That will help in the moment of estimating parameters. Remember that we don't know who alpha is. And we haven't said anything about the distribution of the noise yet. We will immediately convey something. So marginal distribution with other kind of thinnings. I didn't say what other kind of thinnings can we use, but if you use another thinning, then we can have the same expectation for the marginal distribution. The variance will in general change, but Joule and Walker kind of equations will remain. So the autocovariances will satisfy same sort of Joule-Walker equations as AR autoregressive processes in the Joule-Walker style, Box and Jenkins style obey. Okay, so now it's time to say something about the innovations. So as the standard distribution for the noise in Box and Jenkins setup is the normal distribution and nobody questions it. Well, same happens, more or less same happens here. So first choice one has in mind is Poisson distribution for the noises. But we'll see in a minute that it might not be such a good idea to use Poisson innovations, but let's begin with Poisson innovations. So the most popular Poisson in our families is the Poisson in R1 model, where the innovations are distributed according to a Poisson lambda distribution. This is an irreducible and aperiodic Markov chain. So it is a subcritical branching process with immigration. So joining these two things, we have that there is a unique stationary marginal distribution. And since the Poisson is invariant with respect to the binomial thinning, then what we have is that the stationary distribution of in our one process with Poisson innovations is itself Poisson with mean and variance given by, well, lambda divided by 1 minus alpha. And the autocovariance and autocorrelation functions are here. And, well, it's the first time I write it in this talk, even though I said it many times. This is exactly the same shape as the autocorrelation function of an autoregressive process of order 1 in the Box and Jenkins setup. So it's exponentially decaying autocovariance. So what about estimation of moments? Estimation of the parameters, because we have now here an alpha and a lambda that we have to estimate. So first choice method of moments. So the marginal mean is estimated by the sample mean, and the first order autocorrelation is easily computed from the data. So we have an estimation of row 1, and well, all the other perhaps we need other moment relationships in order to get all the other estimations. This is not a nice estimator, but it helps in order, if we want to do some maximum likelihood estimation, then we have somewhere to begin with. So in general, the method of moments is used to trigger up a maximization procedure for computing the maximum likelihood estimates. Another possibility is conditional least squares. Just writing down the difference between the observation and the conditional expectation. So we have to minimize the square difference of xt minus alpha xt minus 1 minus lambda. And well, this is again a minimization problem, which of course doesn't coincide with the maximum likelihood estimators, which is the estimation that we mostly will be dealing with. Well, in this case, in integer AR1 is a stationary Markov chain, so the log likelihood simply can be written in terms of the conditional likelihoods. And well, that's what we do. And either the marginal probability is computed by Monte Carlo simulation, or we just simply forget about this and maximize the conditional log likelihood, this term here. And well, both things can be done. And of course, it's conditional maximum likelihood estimators are asymptotically normal. That's an old result from Billingsley. So again, we have asymptotic bounds for the estimations. We can have confidence intervals for all the estimations. So once we have the process and how to estimate the parameters, let's see it working. So let's watch this example here. If we have time, which I think we will, we can do it live with R. But for the moment, let's just see how things work. So this is the number of weekly cases of human papilloma virus infections in a region here in Catalonia. The data are from 2010 to 2014. Data are publicly available from a government page, which I forgot to mention, but well, I guess I have it written down somewhere if you're interested. So this process, it's reasonably stationary. We can check the rapidly decreasing to zero autocorrelation function. And we have the partial autocorrelation function, which only has a spike in lag 1. So thinking of an autoregressive process of order 1 is not very silly, it looks like. And these are the sample probability mass functions, which should be Poisson distributed. And well, we have to check whether that's reasonable or not. And one thing that makes us think that it might not be very reasonable to have the Poisson model here is that the mean and slightly smaller than the variance. So there might be some over dispersion. In fact, I have done a bootstrap confidence interval for the index of dispersion of this distribution. And I got that, well, one is not there for little, but it's not there. So the data are slightly over dispersed. So maybe the Poisson model is not exactly what we need, and we might have to change the, well, what we can do here is change the type of noise we are adding, the innovations. We can put something that is not equi-dispersed as the Poisson random variables. So, okay, so the series, as I said, can reasonably be considered stationary. Probability, the partial autocovariance functions has a significant value in log 1, so might be a first order autoregressive process, slightly over dispersed. And okay, well, by the way, Poisson mixes are over dispersed. So that might not be so terrible to use this model, but we will see later that there are better choices. Okay, so we have estimated the parameters by maximum likelihood. I'll show you later it's just writing down the likelihoods and pass it through a minimizer. It's the log likelihoods and pass it through a minimizer. It's not very complicated. So what we have is, well, lambda is estimated by 0.18 and alpha 0.7. So the estimated lambda, then the estimated mean of the process will be, well, the lambda over 1 minus alpha, the marginal mean. So the marginal mean is 0.77. That gives us a probability of 0, to see whether the Poisson is okay. One thing we can do is try to compute the probability of the marginal being 0. So that's probability is 0.46, which is kind of big. Well, we have this is the Fisher information, the inverse of the square root of the inverse of the Fisher information. So we have here the standard errors of the estimated parameters. And we have, well, this is the negative likelihood, the AIC and the BIC criterion that we will need them in order to compare this model with something else. But, well, that would do. So, well, after we have computed the estimations, we can check the residuals to see whether the model more or less fits the data well or not. So what we have printed here is the so-called Poisson residuals, the Pearson residuals. Pearson residuals are, well, the x minus the expectation. Let me show you. Let me write down, because I didn't write down what the Pearson residuals are. So let me stop sharing this and share. How do I share something else? Here. Okay, so here we have, well, the Pearson residuals. Pearson residuals are just xt minus conditional expectation divided by the square root of the variance of this. Okay, so these are the things that are drawn there. And under, well, if the model were reasonable, then they would be uncorrelated and with one mean 0 and variance 1. And well, if they have a larger variance, then we would suspect of over dispersion. And the other picture we have in the slides corresponds to the what's called the probability integer transform. That's just take the distribution of xt given, well, xt minus 1, given xt minus 1, we have the distribution of this. And for this distribution, we just do f minus 1. We just compute f. This is f of Rxn xt. And this should be like a uniform in 0, 1. So this is what is, we compute this distribution for each t. So it's different for each t, for each value. But with this distribution function, we make this histogram that we have in the previous slide. Let's go back to the slide. How do I go back? Here. Okay, so what we have here are the Pearson residuals, which look sloppy, but there might not be with variance 1. Variance looks a little bigger. This is the autocorrelation function. This spike is 0, so this is the variance, so it's okay that it's 1. But then the other autocorrelations seem to be 0, so the dependence present in the original series looks like having been taken into account by the model. And the probability integer transform, the probability integer histogram, should look more like a uniform in 0, 1. So this is not exactly okay. This has this U shape that somehow it's indicating us that we have a little of over dispersion in the data that has not been taken into account by the model. So the model, the autocorrelation in the data is well taken into account by the model, but maybe the dispersion is not. So we might be interested on doing something different. And what might something different be? Well, change the innovations. So we could change the Poisson innovations by compound Poisson innovations. In particular, negative binomial, which is a compound Poisson. But any member of the compound Poisson family would do. So the compound Poisson family is essentially the distribution of the sum of a Poisson number of independent count variable, well, of independent random variables. In this case, we are dealing with counts, so count random variables. Compound Poissons are, by definition, they are infinitely divisible family. And we are going to work with the self-decomposable distributions. So when we sum a Poisson number of non-negative integer value distributions, we've seen before that the expectation is the power of the expectations, and the variance is the expectation of the number of things we are summing times the second moment of the distribution of the things we sum. So we have the probability generating function, which is the composition of both, which is, so it's the Poisson generating function computed on the generating function of the X families, which can be written as the exponential of the sum of lambda times the probability mass function of the X times EK minus 1. This comes from the Poisson summation thing. If we have something like this, then we say we have a compound Poisson with parameters lambda alpha 1, lambda alpha 2, lambda, etc. Of course, we can have an infinite number of terms here, but if the alphas cut off after k, after a certain nu, then we call that the compound Poisson nu. And in this sense, well, Poisson distribution is compound Poisson 1. And except for compound Poisson 1, all other compound Poisson distributions with the nu bigger than 1 are over dispersed. So meaning that the variance is bigger than the expectation. Okay, and in particular, the negative binomial, which is the easiest model for over dispersion, or over the dispersion in a count series, is a member of the compound Poisson family, being the sum of a sequence of independent random variables with this probability mass function. So, negative binomial is a compound Poisson. So we can define an over-dispersed in R1 process with compound Poisson innovations, and in this case, the marginal distributions are in the compound Poisson family. That's why they are called self-decomposable. And the compound Poissons are also irreducible and aperiodic. They have finite means, if and only if this H changed its name. Sorry. Well, this is the same H we had before, the sum of the inverses of the weights. And in this case, they have a unique stationary marginal distribution. Again, using that it's a branching process with immigration, we can prove that this is also alpha mixing and it has geometrically decreasing weights. And in particular, negative binomial is a member of this family. And we will see in a minute that if we fit a negative binomial to the same set of data we had before, then the residuals look slightly better than in the case of Poisson in R. So, well, I'm seeing what's the time. Okay, we'll have plenty of time. So we have different estimates here. We go, of course, here we have for the negative binomial, we have the N, we have P, and we have alpha, the thinning parameter. We have the standard errors. We have AIC and BIC, which are slightly smaller than the ones we had before, not much. In the case of Akaike or Bayesian information criteria, the difference between the two models is not very striking. Okay, in this case, different means different zero probabilities, different, you see the innovation zero probability is smaller in this case, which is better. So, well, and looking again at the residuals, again, they are serially uncorrelated, which is okay. Well, there is this high correlation here, but at lag 20 something, which is not really important. And the probability integer transformation histogram is a little bit more flat in this case. So these residuals seem to behave a little better than before. I come from a goodness of fit past. So staying cool just with an histogram of the thing like that makes me nervous. I think this is not enough. But as far as I know, there are no tests for checking whether this distribution has a good fit. I mean, we can do a likelihood ratio test or a chi-square test, which are equivalent, but they are asymptotic tests, and we are dealing with small counts. So we might be kind of far from the asymptotic levels. So maybe not such a good idea. So if anyone wants to develop a goodness of fit test, I guess it would be a good idea. Practitioners don't think that's a good idea. Practitioners adore these kind of pictures, but I guess a test could do a good service to humankind. Okay, so so far models, autoregressive models of order 1. So what next? Well, in order to get something more close to Box and Jenkins family, we need to put moving averages and have higher influence of the past observations. So how do we do that? Well, the counterpart to the usual moving average Q model would be a model with, well, let's thin all the past noises. Well, all Q past noises. But in each instant, we have to thin, well, Q past lags. So in instant T, I have to, wow, I forgot. Well, no, I didn't forget. It's okay. So I have to thin epsilon T, but I also have to thin epsilon T minus 1, blah, 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 at time T. But at time T plus 1, I will be also thinning epsilon T minus 1, blah, blah, blah. So I need to say something about the joint distribution of all the things that are performed over a given epsilon T. The joint distribution of all the thinnings made on the same noise have to be considered. So there are, well, defining different types of joint distribution for these thinnings lead to different models. Most popular ones are the model by Mackenzie, which assumes conditional independence, which is quite reasonable. And again, we have, if we have Poisson of, in all cases, well, we can also assume a conditional multinomial for the thinnings made over the same noise. This is a model by Ranas and Halls and Peter Hall. Well, in the case of independent, conditional independent thinnings, Poisson innovations lead to Poisson observations, for instance. And fortunately, in both cases here, well, a feature of moving averages of order Q is that the autocorrelation functions cut off after lag Q. Well, the same happens here with both, with these two interpretations for the joint distribution of the thinnings made over the noises. So, as I said before, the marginal properties are the same for both models, but the joint distributions are different. And for all of them, the autocorrelation function cuts off after lag Q. And in the case of Poisson Inman model, we will have Poisson observations, and the mean will be just lambda times the sum of the betas. So that's how we can go to MAs of order Q. And what about the autoregressive part? Well, the autoregressive recursion, again, will have to be computed like this. Alpha, and again, the thinnings depend on the time we are using. So at time t, I have a thinning of t minus 1 up to t minus p. And again, since the thinnings are random, the joint distribution of all the thinnings made over the same observation xt at different lags, made at instants t plus 1 up to t plus p, where the xt will have its influence, this has to be considered again, the same way as in the moving average parts. So what happens here? Well, there are, again, different ways of defining what kind of distribution, joint distribution, will this have. And okay, Al-Zaid and Alosh assume that, again, conditional multinomial distribution, and Du and Lee require only conditional independence of all the thinnings that are performed over T. The problem is that in any case, the interpretation of NRP models is quite complex. And choosing the marginal distribution for xt and the noise, again, is complicated. So it might not be such a good idea to use this. I mean, there is not a definite way of defining an NR of order larger than 1. So imagine an inarma of order PQ. Okay, what happens here? Well, in both cases, I mean, asking for conditional independence or a multinomial distribution for the thinnings performed over the same xt, in both cases, the stationary marginal mean is the same, but so far, this is what we get. For the dual Lie, the variances can be computed via this recursion here, and the autocovariance function can be obtained from Joule-Walker equations, the same Joule and Walker equations for an ordinary ARP model. So we can estimate parameters that way. In contrary, if the dual Lie is the one that considers conditional independence of the thinnings. For the other model, the one that considers the multinomial distribution for the condition for the thinnings made over the same observation, well, this doesn't have the ACF of an RP, but rather an ARMA PP minus 1. So the kind of autocorrelation does not behave like the one we expect for an integer process of order P. On the other hand, if we choose the multinomial, then for Poisson innovations, we have Poisson observations, but if we deal with the conditional independence, then we lose the property which having for the dual Lie, we do not have conditional independence. Okay, anyhow, people normally uses the dual Lie in our process, and mixing and weak dependence properties were proven by Paul and associates. So any questions on the subject directly to him. Well, it seems that the chapter of defining thinning-based models of order bigger than 1 is not quite closed. So there are different things. In the case of dual Lie, for instance, the problem is that the transitions are convolutions of P binomials, which come from the P thinnings. So that's why the ACF is kind of complicated. But it can be done, but the marginal distribution is kind of well, ugly to compute. In any case, estimations can be done. In fact, in Weiss's book, there are lots of R code for doing that. I'm not sure if they are in the book or they are in some web page somewhere. I have the codes, so and I got them from Weiss. So these codes are written. It doesn't exist an R library in order to do that. Well, we have 1 more hour, and we will have to talk about conditional regression models, which is a completely different subject. So maybe we can shut down the slides for a while, and if you have some questions, or shall I go on? What do you think?
It's really up to you.
Really to the public, if it's still alive?
Most of them.
Okay, well, so let's go. Okay, so another way to circumvent the problem of multiplication. So conditional regression models. It's I guess it's more flexible than the previous one. both methods have advantages and disadvantages, but well, this conditional regression model allows, for instance, nonlinear forms of dependence, which is possible via generalized linear models, which is a good thing to have. And the basic idea here is to transfer the ARMA recursion to the level of conditional means. So it's the conditional means which are going to be the ones that depend on the past and on the previous innovations. Since the mean of a count random variable is not necessarily an integer, in order to avoid the negative outcomes, you have to ask for some constraints on the parameters, but not so complicated. So what do we have? So an INGARCH PQ model is, well, use a linear or nonlinear regression for the conditional mean, the mean of xt given the past. For instance, an autoregressive of order 1 in this world would be, say, that the conditional mean, that the mean at time t is beta 0 times alpha t minus 1, and the count time series is then generated by using a Poisson random variable with that mean, or a negative binomial satisfying some, well, n times p over 1 minus p has to be adequately defined. So what we have are, the outcomes are integers, and what changes here is the mean of the observations. Okay, so why we call this an INGARCH? Well, because one thing which is very important, this is not a universally accepted name. There are a lot of people that call this just conditional autoregression and not INGARCHes. A GARCH, an arch process, is an ARMA for conditional means. For conditional variances. So in this we have a recursive scheme, not for conditional variances, but for conditional means. So GARCH is not really a good name. GARCH, the usual GARCH, is a generalized autoregressive conditionally heteroscedastic model. So here, there's no conditional heteroscedasticity. Well, there is, but we are not going to model it. We are modeling the conditional mean the same way that arches and GARCHes model conditional variances. So maybe the idea of INGARCH is not such a good name. Okay, so INGARCHes, this kind of models, I say that the name is not usual, not the one that people use, but I'm going to use it. Well, these models are fully specified if the conditional distribution of xt given the past is fixed. So again, the easiest choice is to assume that they are Poisson distributed. So the conditional distribution of xt given the past is a Poisson with distribution with mt as the variance, and mt will be a linear combination of p past lags. And okay, we have to put certain restrictions. The sum of the alphas has to be smaller than 1. This is a pth order Markov model. In general, well, this thing is usually, a model like this is usually called a linear Poisson autoregression, okay? In particular, for p equal to 1, the transition probabilities are very easy to compute, and you need them for doing maximum likelihood estimation. Conditional mean and variance coincide. They are both linear on the previous observation. Again, it's a stationary ergodic alpha mixing Markov chain. All moments are finite. And well, in particular, the mean and the variance. The mean is the same mean as in the, well, has the same form as in the other setup. In fact, if we choose the same alpha and beta equal to lambda, then the INR1 and the INARCH1 have the same mean and marginal autocorrelation. One nasty thing about this is there is no closed formula for the stationary marginal distribution. And in this case, we have here this 1 minus alpha here gives us conditional over dispersion that increases with alpha. And in GARCH processes, the GARCH1, the Poisson in GARCH1 usually has sample paths that have more extreme counts than in the Poisson in R1 counterpart. Of course, the INARCH1 model can also be combined with non-Poisson conditional distributions. For instance, if we choose again a negative binomial, we can achieve more over dispersion. I think I don't have a, did I write it down? No, I didn't write down a slide with the, let's write it down because it might be of some use. Let's go back to the blackboard, whiteboard. How do I erase this? Just erasing it? No, here, clear all drawings. Okay. And again, draw. Okay, so what was I going to do? Okay, well, I have to put, I said that I can define an INGARCH, well, an INGARCH1, say, with the negative binomial, say NTP, where now NT is the one that's going to be MT times P1 minus P, and MT again. Say beta 0 plus alpha, well, beta plus alpha, MT minus 1, or a larger order INGARCH. But if we put just, and if we take an auto-regression of order just 1, then sigma square in this case would be mu over P1 minus alpha, and change in alpha gives us extra over dispersion. So that's, no, P. The alpha is same as before, as we had before. So P here gives us an additional dispersion parameter. Okay, so let's get out of the whiteboard and back to where? Back to here. Okay. So, well, we can compare Well, we can have this with orders P and Q. So just as Garch extend arches by adding information on previous noises of conditional variances, well, we can have here feedback from the previous conditional means. So again, we define here the Poisson in Garch model of order P and Q by saying that xt conditioned on the past is Poisson with mean mt, and mt, the conditional mean of xt given the past, is a linear combination of the past observations, p past observations, plus conditional, wow, there's a typo here. This is the noise. This is not x, this is epsilon, t minus j. This is a copy-paste thing. So, okay, here, well, sorry, you have to correct it. Well, the expectation here, even though the conditional distribution is Poisson, the marginal mean is always, the marginal variance is bigger than the marginal mean. So the Poisson in Garch models are suitable for over-dispersed data as well. Okay, it can be shown that if the sum of the coefficients is more than one, then there is a stationary solution for this recursion. Well, the mean will be the beta 0 over 1 minus the sum of the alphas minus the sum of the betas. This is just the same thing that happens with a real Garch. Okay, and variances and covariances are determined by a set of Joule and Walker equations. So, well, that helps in computing moment estimators and things like that. They don't help. Joule and Walker equations are useless for estimating parameters except for purely autoregressive models, because when the means are involved here, when the betas appear here, then we can find the equations that cannot be really solved uniquely. So they don't help much. And okay, as I said before, the Garch model can also be done with a negative binomial. I thought I hadn't write these down, but I did, sorry. I made you lose your time with the blackboard, quite well. Okay, so to round up things, how do INARMA and INGARCH compare? Poisson regressions and INARMA. Okay, so both are ARMA-like approaches for modeling count-time series, and the pure autoregressive members have identical correlation structure. On one hand, marginal properties are easier to derive for the thinning-based models, but conditional distributions are much simpler for the conditional regression models. For instance, the transition probabilities of Poisson in Garch are just Poisson probabilities. And the transition probabilities of the Poisson in ARMA, in R, the thinning-based, are just convolutions of, of whatever we are summing up there. So conditional distributions are quite easier in the case of INCARCH because you just declare them. In ARMAS, the thinning-based models include pure moving average type models, and the INCARCH don't. So a little bit worse than that, the moving average part in an INCARCH somehow produces long memory because the observation is affected by all previous information. For instance, for the INCARCH1, something like this ends up appearing. Okay, something good about both is that both can be adapted to non-stationary data in different ways. Somehow, INCARCH family is a little bit more flexible. Adding information here, especially on past lags, is much more easy in this setup than in the thinning-based case. That being said, what I'm going to tell you next Monday, if you still bear with me, is all based on INARMAS. But okay, so well, what happens with the data we have been studying before in this setup? Well, conditional regressions are very easily fitted because there is an R library that does the trick. It's a library, well, by Focianos and Associates. The name of the library is tscount, and it's kind of easy to use. The only thing is that you rely on the notation we have been using. It's kind of different of the one that it's used in the library, but the model can be very easily well, fitted. So you see, it's just this instruction, TSGLM. You have to put the data. Data is the name of the vector where the data are. And the model, okay, you say how many past observations, and the distribution Poisson. You can put also a negative binomial if you want. So, well, we have here the model fitting. It doesn't make much sense to compare these numbers to the numbers we have obtained before. These are larger, but they come from an absolutely different world. So it doesn't make much sense to say, oh, I'd rather get the other one because it's smaller. We can do the same thing we did before. Again, Poisson residuals here. More or less, they look the same, more or less have the same variance as the ones we had before. Autocorrelation function gives that data are non-correlated, except again here in this lag. I don't know what happens in this lag. And then the probability integer transform here gives more or less the same problems that they had before. I mean, meaning that we have still some over dispersion problems. And if we change it to the negative binomial, the INCARCH with negative binomial again gives us slightly smaller AIC, slightly smaller than the Poisson one, than the one we just seen. With the, well, we have this parametrization here for the negative binomial, and the again, the autoregressive structure of present in the data has been captured by the model, and the problems with the overdispersion seem to have a better fit with this model than when the one before. And well, what else can we do? Well, lots of things can be done. For instance, generalizing this by putting log linear Poisson autoregression, Fouquianos. This is sort of a multiplicative model. Okay, if you put take the exponential of all this, you have a multiplicative autoregressive model. Some sort of yeah, of multiplicative Ingarch. Okay, in order to guarantee the existence of a stationary distribution, of course, you have to ask for certain things. For instance, in case of this model, you have to ask that, well, the sum of alpha and this beta is in absolute value smaller than 1 if alpha and beta have the same sign, and otherwise you have to ask that alpha square plus beta square be smaller than 1. I'm quoting by heart, so maybe I am mistaken, but I guess this is it. Also, you can add covariates, for instance, to deal with linear trends or harmonic oscillations. And for instance, this model by Ziegler and well, it's this proposition is for, it's kind of old, but it works for seasonal models. This has a linear trend and a couple of harmonic oscillations. You can add them to the model as covariates and fit the model like that, and then you can deal with things like this. For instance, these are weekly counts of some bacteria that causes diarrhea. And well, you can see here a clear seasonal pattern. And in order, well, maybe an increasing trend, but very slight. So we can try, well, this is the autocorrelation function of the data, which is clearly the autocorrelation function of something that is not stationary and periodic. So, well, we can fit this log linear model. We have some parameters estimated there. And if you see, well, the Pearson residuals, you can make a portmanteau test on the residuals. The length I took a year for the 52 weeks for making the test of the residuals. So the squared residuals are independent according to Jung box test. And well, you see the black thing is the original data, and the red is the marginal mean. And well, the marginal means, the MTs, are approximate, well, nicely the oscillation of the data set. So well, this model works, and which is something, I don't know what's the time. I should be ending now. I should, if I find the R code for that, which is very simple because the library is very flexible. Where do I have that? I'm not really sure. I know where do I have this conditional regression here. No. No. I don't know where did I put the code for doing that. I have so many R codes. I should have looked for it before. Well, so well, I guess this is it. Unless you have questions, doubts. Still there? Still alive?
No, yes.
Completely asleep?
Do you? So I didn't understand really well what you said about INAR with higher order. So you said that there is not much work on it, or
Much work on what?
on those INAR with memory more than one. You said, I am not sure.
No. Yes, there are things, but what I said is that there is not a definite definition. There are 3 or 4 ways to put the moving average part, 2 ways at least to put the, so people don't agree on what should be an INARMA process.
Yes, sure.
So that's a drawback.
Are there questions?
Yeah, I have a question.
So you have the answers.
Okay.
You work on this subject more than I.
No. I think it's a question I noticed with these INAR models. For instance, this model are the analog of the autoregressive process for continuous data. So it is exactly the same kind of autocorrelation function.
Yes.
But the main difference is that these models are conditionally heteroscedastic in the sense that
yes,
you have a conditional variance which is stochastic.
Yes.
So it means that when you have a large count, the conditional variance will be large, and then the prediction will be more imprecise.
A disaster, yes.
Yeah, and I was wondering if this conditional heteroscedasticity is what we find on real data, because sometimes I had this experience, so I just share my experience about this if you have the same experience. For instance, when we try to estimate the mean of the counting sequence and the mean of the epsilon, so you subtract the conditional mean, and then you apply a double least square to estimate directly the variance of the counting sequence. And sometimes on real data sets, I noticed that this variance is very small, and sometimes so small that it is not compatible with an integer value counting sequence. And so I was wondering if there is a debate about this, because you have a kind of conditional heteroscedasticity, which means that it is exactly as for arch processes. So when you have big changes, it will be followed by big changes. And is it really the most compatible with real data, or?
I don't think so. You need your data to be really, I mean, not having really stationary. If you have those big counts, then everything goes to hell. That's
okay.
Even the estimation of the parameters is a disaster if you begin to find large counts. So yeah, that's why I think that the INGARCH or the conditional regression models are more flexible, because they can handle all that kind of problems.
Yeah, okay.
On the other hand, the conditional distributions, well, are what they are. So I'm not really sure this is over. I mean, the count time series problem.
Oh no, I think, yeah, because at the beginning, this model were developed. So first, with respect to the modeling of the marginal distribution, and also at the same time, the first order correlation. But these were the two main reasons at the beginning. And of course, it is to put some models that send the integers over the integers. It imposes a kind of specific structure and a strong structure, in fact. And, but I didn't, for instance, I didn't find many works in which they compare the forecasting with the error in forecasting, comparing, for instance, a classical model for continuous data, even if it is here it's for integers value, it doesn't matter, to compare a classical AR model or ARMA model with the in-ARMA, for instance.
I don't think there are. I mean, there are very little thing about forecasting, because forecasting in the end is with the conditional means anyway.
Yeah, but the conditional variance or deterministic variance will not have the same impact, because sometimes we will produce very large confidence interval and sometimes
yeah, but the forecasting is mainly done through the conditional mean thing, and nobody says anything about the variance.
Yeah, okay.
Not as far as I know.
Okay. Yeah, this is what I noticed also.
I mean, I didn't say anything about forecasting. I had my forecasting example, which is a disaster. In fact, I have it here. This is a sorry. Here, I've lost it. I was, and it's more or less what you say. Let me, where is it? Share. Share here. So this wasn't, you see in the R, right? Yeah, this is an example of a forecast distribution. This is the observed marginal, and the gray things are the forecast, and you see it begins to fail up to a certain point. And this is with the negative binomial. This is the negative binomial. I'm not really sure. I was.
You mean the long horizon prediction?
Yeah.
Yes, since it is a short memory model, it is not surprising.
So this begins to, the farther you are, the forecast begins to overestimate what's going on. Perhaps it's reasonable, because it's hard to forecast large values, but I'm not sure. I had the other forecast? No. Or this is, no, yeah, this was the negative binomial example. So, well, I've lost the Zoom here. Stop sharing. Well, so.
Okay. So
this is it.
So so we meet next week. That's it. Okay, and so also don't forget that there is also the second lecture by Gilles on next Monday in the morning. Okay. So thank you very much for giving these lectures, and thank you very much for all of us, all of you to attend it. So goodbye.
Bye.
Thank you. Bye.